So, a very good evening to all of you. This will be the last lecture on chemical measure trace and ultra trace analysis, and that will again finish the total course of advanced material chemistry. So, again, let me tell you, this is my mail address, and I am yet to receive any mail or any query from all of you. I hope everything is quite clear and you will be able to do the assignment very well. So in this lecture, we will be covering the last part, neutron activation analysis and X-ray fluorescence spectrometry. So again, the neutron activation analysis and X-ray fluorescence spectrometry. So this is just a periodic table, which is given here to show you that bulk, biological elements, trace elements, and possibly essential elements for a biological species, just like that, the periodic table, because periodic table is a very avoidable part for an analytical chemist, and therefore I have just put it here. So now, before going to the neutron activation analysis, we must know these things, and I am very well aware that you must be knowing these things. So this is a notation, general notation of an element, where X is the chemical symbol for the element, A is the mass number, which is nothing but the proton number plus neutron number, and Z is the atomic number or number of protons. So again, like for example, this is nitrogen 7 and 14. What is a nuclide? Nuclide is a particular type of nucleus characterized by specific atomic number and nuclear number. And nuclear numbers means mass number, that is the number of nucleus, proton and neutrons. Means what are the particles present in the nucleus, that is the nucleus. And you must be aware of isotopes, isobars and isotones. So isotopes are having the same Z but different mass, like atomic number same. So means it is a same element but having different mass number because of presence of different number of protons, different number of neutrons. And then isobars are nothing but different elements having same mass. So those are the isobars, and isotones means same number of neutrons. Elements where the number of neutrons are same. Neither the proton nor the mass number, but the number of neutrons are same. Those are called as isotones. So with this, let us look about radioactivity. What is the radioactivity? Radioactivity occurs when an element's nucleus is unstable because the Coulomb force between protons and attraction force between the neutrons are not in balance. So radioactivity is classified into three types based on the radiation or decay, like alpha decay, beta decay, and gamma decay. Now the radioactivity is evaluated using a standard unit known as becquerel. You all must be aware of that. So denoted by BQ, the name for the physicist like Henry Becquerel. So this is given as the unit of radioactivity. So this Curie, and then this is the Becquerel. So one Curie equal to 37 billion Becquerel. So all these things you have to be aware of while doing a neutron activation analysis. So where at all an element becomes radioactive, because if there is an imbalance between the number of proton and neutron. See, up to Z equal to 30, up to Z equal to 20, N by P is exactly equal to 1. When Z at Z equal to 30, N by P ratio is 1.25, mean number of neutrons are increased. So slowly the ratio becomes 1.5, 1.25, 1.4, and then 1.5. So you can see this is the ideal line. And beyond this, if an element is there, that means number of proton is more, then it can undergo like electron capturer beta plus, and that is unstable. And if in this side it is like number of neutrons are more, then it will be undergoing a beta minus decay, so that they are tend to bring their N by P ratio as closely as possible to 1 to attain the stability. So now, what are the various types of radioactive decay? Here are our list. The alpha decay. You all know about this. You have to go through alpha decay, beta decay, positron, proton, neutron, and gamma rays. So these are their characteristics listed here in the form of a table. So beta decay of a neutron, actually what beta decay, where from that beta is coming in a nuclear decay, because it is not a part of the nucleus. But yes, beta decay is coming from the neutron itself, where it is the neutron is dissociates into proton, and some antineutrino will be coming out. So beta decay of a neutron transforms it into a proton by the emission of an electron accompanied by an antineutrino. Similarly, converted into a neutron by the emission of a positron with a neutrino. So that is where they are coming from inside the nucleus. Now, nuclear analytical techniques. What are the various nuclear analytical techniques which are based on this radioactive property of an element? So it is deals with radioisotopes, tracers, or induced activity or measurement of radiation. So direct methods are there where you can measure the natural radioactivity of a substance like uranium and all, and you can calculate their concentration. Like for uranium, track detector is there, which uses its fission property to calculate its concentration. Then indirect methods are there, where activation methods are there, prompt gamma, delayed gamma, then ion beam analysis like nuclear resonance analysis and a PGE, RPS, PIXI. Then addition of radio tracers are there, use of various radiation sources are also there, absorption, scattering analysis, fluorescence, so XRF. So we will be looking into this and looking into the NAA. These two in details we will be looking into. So now, what is a neutron activation analysis? Neutron activation analysis is a powerful isotope-specific nuclear analytical technique for simultaneous determination of elemental composition of major, minor, and trace elements. It can, like this technique, we can cover the whole range of percentage to ultra trace level. So you like this will be well to mention here that this is the scientist. And then his assistants, Hilde Levy, they were the first to introduce the neutron activation analysis in 1936. So this is the George D. Hevesy, and this is the Levy, Dr. Levy, who has assisted Dr. Hevesy in determining like neutron activation analysis. And for this, he got the Nobel Prize in 1943. So now what is neutron activation analysis? Neutron activation analysis is a method for quantitative as well as qualitative determination. It is a qualitative as well as quantitative determination of elements based on the measurement of characteristic radiation from radionuclides formed directly or indirectly by neutron irradiation of the material. So let us pictorially look into it. This is a target element which is non-radioactive, which is stable nucleus in which a neutron is getting bombarded. Then a compound nucleus is formed, and by gamma radiation emission, it comes to forms a radioactive element. So here the gamma which are coming out of this compound nucleus are prompt gamma radiation. So these prompt gamma radiation are also being used for analysis of some elements. Then now after absorbing that neutron, because now the proton and neutron balance has been not there, so it becomes radioactive. Now this radioactive material tends to decay, either beta particle decay will be there, and then this radioactive decay, due to this, again it will transform to an element, say X star, and again now it is in excited state, which will emit one gamma radiation to form a stable nuclide. So this is the delayed gamma radiation. So now you can see during this process, your element will be changing from X to here. Now one neutron is coming, therefore its mass number is increased by 1 unit. So now, so then again, this is the same. It is in excited state and it is in ground state. By emitting one gamma radiation, it has come to the ground state, and this is the prompt gamma radiation. Now again from here, one beta particle has been gone through, and therefore beta particles. So now is this proton number has been increased or decreased by 1, and then so this is the ground state atom by giving the delayed gamma emission. So now neutron interaction often produces radioisotopes. Entire periodic table can be covered by Na. So this is the potential of Na. So now you see again that has been like neutron. This is the element. Then prompt gamma analysis will be there. Then delayed gamma. This is DGNA is delayed gamma neutron activation analysis. So now, according to the type of emitted gamma measured, so it can be of two types. If the prompt gamma ray is measured, then radiation, then it is the prompt gamma NA or PGNA. So the measurement takes place during irradiation itself. So detectors are placed very close to the sample, compensating for much of the loss in sensitivity due to flux. So now the second one is the delayed gamma. It is delayed gamma neutron activation analysis of DGNA. The measurement takes place after a certain decay period, because when the sample is irradiated as such, because of various elements present, it can gain high activity. Like if it is containing sodium, then sodium can get very high. So you have to allow it to decay for some period, and then you have to bring it to your lab, and then you can measure the various radiations coming out of this, which can give you an idea of the element present in it. So now let us look into the methodology for NA. So you have to call, these are the common methodology for all the analysis. In this case, now you have to collect the sample, you have to prepare the sample for irradiation, because it is not as simple as like you are dissolving the sample, you are going to put the sample in a nuclear reactor. So you have to prepare it properly for irradiation, then preparation of standard, then irradiating using a neutron source, mainly a reactor, then bring the sample for counting, activity measurement, spectral analysis, concentration calculation, evaluation of error, and interpretation of result. So care has to be taken at each step before interpreting the result. Now, some important factors to be considered during this process are the neutron source. You have to get a good neutron source having high flux, because the more is the flux, more will be the sensitivity. Maximum low energy neutron component, fast access to the sample, because once the samples has got irradiated, you have to bring that sample as soon as possible to your lab for counting. So fast access to the sample, provision for irradiation of different size of sample has to be there. High resolution gamma spectrometer is needed. Low background spectral analysis software has to be there. Then preferably Crompton suppression spectrometer has to be there. Then sample preparation, reproducible sample detector geometry, and then you have to look into the whatever result you have got, you have to analyze it for its quality of result, whether it is you have got a true result or is there some bias to the result. So you have to evaluate all those things. Now these are the various research reactors available in DAE for like here within BARC for irradiation of your sample for neutron activation analysis. Now this is not operating now, and this also has gone. So now Dhruva is there, these are theirs, and all these things are there now. The new Apsara has come, in which the samples are now being irradiated. So the research reactor facility, some pictorial has been given here, and normally for Dhruva reactor or Cyrus reactor previously, there is a pneumatic carrier facility through which the sample has to be transported into the reactor for irradiation. So you can, because you know reactors are very, like there will be high radiation, so person cannot go inside the reactor to put the sample. So there are pneumatic carrier facility. Pneumatic carrier facility means your sample will be automatically transported into the inside the nuclear core, the reactor core for irradiation. And the neutron flux is around 10^13 to 10^14 neutron per centimeter square per second. So this is the unit of neutron flux, neutron per centimeter square, like neutron per unit area per unit time. So it is neutron per centimeter square per second. So flux is around 10^13 to 10^14, very high flux. It is good for NA analysis. Now the measured activity, like activity, whatever after the neutron irradiation, the activity, whatever you are measuring in the sample is related to this equation. Now it is a long equation. You can see here, A is nothing but activity counts per seconds. Whatever your sample is getting activated and what you are measuring it in a detector, like what is the activity. So that from this detector only you are getting the activity. N is the number of atoms in the target, means your analyte atom. So phi is the neutron flux. Sigma is the reaction cross section of that element what you are going to analyze, like what is the analyte, its neutron absorption cross section. T is the irradiation time, TD is the decay time or delay time. Now decay constant of the radioisotopes formed, lambda is the, and CT is the clock time, LT is the leaf time, gamma ray abundance, and then detector efficiency. So all these factors are there, of which many things are constant. So, and few things you are getting from your counter itself, like your detector. So you can calculate the concentration of your sample. But two important factors for an element to be determined in NA is the parent element or isotope should have appreciable neutron absorption cross-section. Otherwise, it will not absorb and it will not be getting converted into any form that can emit your gamma radiation. Therefore, it should have appreciable neutron absorption cross-section. Also, radioisotope formed should have measurable half-life. Otherwise, again, you have to, like, if it does not have a measurable half-life, so it will decay very fast. So once you are bringing it to your lab, then itself its activity will die down. So you have to look into these two factors. Now the multi-element analysis, simultaneous measurements of various gamma rays having different intensities and energies and determination of several gamma emitters can be done simultaneously. Therefore, it is a multi-elemental technique. And for the same irradiation time, by judicious selection of decay time and counting time, as many as 30 to 40 elements can be determined at the same time. So these are the list of elements, and this is the detection limit what is obtained in your in neutron activation analysis, and you can see all are in either picogram or PPT, nanogram level or picogram level. So now this is a periodic table, and there is a color code which shows the various, like conventional NA and PGNA. The detection limit is around 0.01 to 1000 ppb. So the red color are amenable to prompt gamma neutron activation analysis. The magenta color, these are instrumental neutron activation analysis. Now the blue color, like these are the fast neutron activation analysis, means your fast energy neutron has to be bombarded on that. So like this with color code, this is the periodic table which you can look at one look, you can know what are the elements and which can be done by neutron activation analysis and what are their detection limits. So now neutron sources, which are the neutron sources? Normally neutron sources, because now as you have seen, your sample needs to be irradiated by a neutron. So you need a neutron source. So neutron source can be nuclear reactor, it can be radioisotopes which gives neutron, or it can be neutron generator like accelerator based. So let us look into. So now the normal neutron activation analysis or delayed gamma neutron activation analysis, sometimes called as NA also, is useful for the vast majority of elements that produce radioactive nuclides. Now the technique is flexible with respect to time, such that the sensitivity for a long-lived radionuclide that suffers from an interference by a short-lived radionuclide can be improved by waiting for the short-lived radionuclide to decay. So this is the self-explanatory, like if there are two elements, one is very short-lived and one is very long-lived, then short-lived will be will get activated very highly. So you have to wait for some time so that its activity will die down, so that you can do your analyte in a good manner without with less interference. Now this selectivity is a key advantage of DGNA over other analytical methods. So now there are three types of neutron activation analysis. Like in delayed gamma neutron activation analysis, there are three types. All are given here. Like so, instrumental, radiochemical, and chemical. So it is generally possible to simultaneously measure more than 30 elements in most samples types without chemical processing. However, so the application of purely instrumental procedure is commonly known as INAA or instrumental neutron activation analysis. Whereas if you need a chemical separation after irradiation due to some interference, so that will be called as radiochemical neutron activation analysis or RNA. And if you need to separate before analysis, because something is there present which are going to be very highly activated, which can create in sample handling after irradiation. So you have to separate that beforehand. So before irradiation means it is before irradiation, this is after irradiation. So it will be called as chemical neutron activation analysis. So when it is after irradiation, it is radiochemical neutron activation analysis, and before irradiation, it is chemical neutron activation analysis, or CNN and AM. So now let us see the NA procedure again. So sampling, pre-irradiation sample treatment such as cleaning, drying, ashing, pre-concentrate of elements of interest or elimination of interfering elements, subsampling and packaging, irradiation and prompt gamma counting if it is required, then radiochemical separation if required, radioactivity measurement, then elemental concentration calculation, and critical evaluation of results and preparation of the NA report. So let us see one by one actually sampling. So say you want to measure some elements in this plant sample. So you have to obtain the plant sample. Okay, you obtain that. Then you have to wash the sample to remove all possible contaminants, because you know when it's a plant sample, there may be deposition of various dust particles on the plant sample. So if you are not washing it properly, then they may contribute to your analyte if they are containing the analyte. So you have to, otherwise also the soil and dust will contain high amount of sodium, which will get very highly activated. So therefore you need to wash and properly dry the sample. So now you can dehydrate the sample. Dehydration methods use heat or freeze drying, or a lipophilizer also is frequently used for the freeze dry method. A plant sample is then placed in the chamber atop the lipophilizer to the right hand side, and then this is a typical picture, and it is getting dry. So now the dehydrated sample is then prepared for testing. So a small amount of the dehydrated plant material is removed from this bag. Now you have dried it. Now a small amount is removed, and then you have to properly grind it for homogenization. So a portion of the dried material is ground into a powder using mortar pestle, because it is very much required to ground this, because after drying also it is not homogeneous. There are stem and leaves, they are separately present. So you have to grind it to a particular powder form. So sterile technique is required to avoid cross contamination, also has to be avoided here. So now after proper powdering it, the powder is packed in polythene like this type of plastic envelopes. So now once you fill the sample, and again the envelope will be put in another envelope. So double bag, and then you level it properly. So now select a standard comparison, because if you want to compare your, you want to have a comparative method, you have to take some standard also. So it is a plant sample, you have to take some plant-based standard. So you have to select a standard for comparison, and you may take a certified reference material also. So these are the various standards kept in a desiccator. So now then both the packets will be put in some plastic vials like this. You can see the plastic vial is hardly around 2 inch of height. So both the packet, the standard as well as your sample, they will be placed in the in this plastic bottle or capsule, that is called as sample capsule, and then properly the cap has been put. Now the sample has been taken to, say, Dhruva reactor, and then you have to use the pneumatic carrier facility, where like it is called as a red bit. Actually the thing which is going inside the reactor to put the sample is called as red bit. So there you have to put your sample, and then it will be through pneumatic facility, it will be sent to the reactor core. So after irradiation of the, there you have to put the sample. This sample will be there for a predetermined time required, because depending on your analyte, you must have been calculated how much is the time required for its irradiation. So then for that amount of time it will be there, and it get irradiated. After that you have to bring back the sample to your lab for its counting. So after irradiation of the sample in the capsule, and before removing it from the reactor site, it must be determined if the capsule is safe for transfer. So a GM counter will be used for that, to look into the how much activity is there in the sample, whether it is safe to be transported to your laboratory. So now you have to measure the radioactivity. So the instrumentation used to measure gamma rays from radioactive sample generally consists of a semiconductor detector, associated electronics, and a computer-based multi-channel analyzer. So now most NA labs operates one or more high-purity germanium detectors. Now again the NA is divided into three types: INA, RNA, and CNA. So now instrumental neutron activation analysis, the salient features are: it is non-destructive, free from reagent blank, fast and simple. So now your example is trace elements in leaf, whatever I have shown you. Disadvantage is matrix interference or high matrix activity. Like if your plant sample and all contains sodium, so it will get very highly active. So that is the, then even you can do gone short residues like barium, antimony, and rare earth in uranium. So in case of rare earth elements in uranium, the matrix separation is essential. So here you have to go for CNA. So beforehand you have to separate the matrix. So you have to go for CNA. So now matrix separation, as I have told you earlier, so before irradiation, after irradiation, it is CNA and this is the RNA. Now RNA advantage is that free from reagent blank, because you are irradiating your sample and then you are processing. So whatever contamination, it will not be getting activated because you have already irradiated the sample. So that will not affect, because you are going to finally count the gamma rays, and gamma ray will be coming from the samples which is being irradiated only. So it is very safe and there is no reagent blank will be so free from interferences due to matrix and other elements. For example, like barium and antimony in concert residue, they are done by RNA. So now the concert residue is irradiated, radiochemical separation of barium and antimony. So precipitation you can do, and then you measure the gamma activity measurement. Disadvantage is handling of high matrix activity. So because when you are separating your element of interest after irradiation, so you are handling the whole sample as such, which are highly active because of irradiation in your neutron source, in a neutron source. Therefore, you are handling the high activity of matrix. So CNA is the before irradiation. So higher sample size you can take very like you can pre-concentrate properly, because you can handle high volume of sample, and you can separate your element of interest from that, converting into a small size, so that there will be a pre-concentration factor which can allow you to low detection limit. And also because before irradiation you are separating the matrix, so you are handling low activity. Example is impurities in uranium. So separation of impurities, irradiation, then gamma activity measurement. So free from interference due to matrix uranium. Disadvantage, not free from reagent blank, because again you are doing the separation before irradiation. Therefore, there is a chance that whatever impurities or blank they are getting added in the sample may contribute to your signal. So there can be a chance of contamination in this case. Now, what are the various sources of errors in NA? Like it can be either sample preparation. So during sample preparation, there can be contamination, and especially when you are using your chemical NA, like separation of matrix is before irradiation, then contamination of the sample may happen. Then there can be inhomogeneity, as you have seen the plant stem, whatever is there, the sample, plant sample, which contains a leaf, stem, and other parts. So now the element of interest or your analyte of interest may have different concentration in leaf and in the stem. So if you are in total, you want to know your analyte, then you have to homogenize the sample properly. So there can be inhomogeneity if grounding is not proper or homogenization is not proper, then it can lead to some error in your NA. Then weighing also, if sample is not properly weighed, because in the NA equation you have seen that weight of sample also is a parameter. So weighing is important. So now any anomalous isotopic abundance, or if it is a not natural sample, it is a depleted sample of uranium or any different isotopic ratio other than natural is present, then you don't have a proper standard for that. So in that case, there can be error. Now neutron flux perturbation, you are like you are assuming that the neutron flux is 10 to the power 13. Throughout the sample, it is getting 10 to the power 13 neutron per centimeter square per second. But it may be different, or sometime it may face some different flux. So then it also can contribute towards the error. Now, interfering nuclear reactions can also happen, or any spectral interference if some other element also is very close to the gamma spectrum of your interest of analyte, then there can be spectral interferences also. So now the limitations of NA is it requires a reactor. Now very short-lived or very long-lived activation of products can be there in your sample. So it will be very difficult to like you have to irradiate your sample for different time for analyzing or for quantifying the short-lived and then very long-lived. But once for very long-lived, if you want to irradiate it long time, then that time the short-lived nucleides will be very highly activated. So then it can create some issue during your analysis. Now, chemical speciation is not possible because it will be the total sample only you will get. Like chemical speciation you have seen in case of electrochemical analysis. You can do the chemical speciation, but here NA is not, it is not possible to do chemical speciation. Now, conventional Na is not suitable for all the elements like just small Z elements like hydrogen, carbon, boron, lead, etc. Because lead is a very stable isotope. So it is having very low neutron absorption cross-section also. So it cannot be done because the first thing is that your analyte also should have a very high neutron absorption cross-section so that it can absorb a neutron and then it can get converted to some element which has radioactive property. So now gamma ray spectrometry. Again, after irradiation, you have to subject your sample to gamma ray spectrometry. So high resolution detector like HPG is used. Good detection efficiency 10 to 100%. Or multi-channel analyzer is used. It is good shielding has to be there, and the person who is handling this type of radioactive sample should follow a good laboratory practice. So good electronic accessories and spectral analysis methods are very important in addition to good laboratory practice. So for NA, SPG detector is preferred due to better resolution. So this is a typical setup for SPG detector, which is needs to be cooled by the nitrogen container is there. So because it needs cooling. So now three methods for concentration calculation. One is the absolute method. Absolute method, no standard is required because in that equation you can see sigma, phi, all these things are like fixed only, like constant only. So you can directly calculate the concentration. But it is normally not used as though for a reactor neutron flux and for an element the reaction cross section should be fixed, but then you never know how it is fluctuating because your sample it is in a different shape. So whether in all the place it is getting the same or not, it is very difficult to know. So therefore normally relative method or comparative method is being followed. As you have seen in the small plastic bottle, both standard and sample both has to be filled so that they will face the same environment, and therefore you can compare their counts or 1 to 1 for a better like true value, to get a value which is more close to the true value. Or another method is single comparator K0 method, where this gold, manganese, or scandium are taken as the mono standards. So this is out of scope of this lecture. I am not going into details. So now sensitivity in case of Na depends on theta, sigma, phi, epsilon, and gamma. Of this, these two are the very important point: neutron flux and efficiency of the detector. So these two contribute the most, whether it is depending on the all these things. Your sensitivity and what are these parameters are given here. You can go through. So now detection limit. What is detection limit? It must be remembering from our initial classes, because I have taken the detection limit in broad way in my initial classes. So detection limit represents the ability of a given NA procedure to determine the minimum amount of an element reliably. So detection limit depends on, in case of NA, it depends on the amount of material to be irradiated and to be counted, neutron fluxes, duration of the irradiation time, total induced radioactivity that can be introduced in the sample after irradiation, duration of the counting time, and detector size, counting geometry, and background shielding. So all these factors are there who can affect your detection limit. So now application of NA can be applied to various things like biology, forensic science, nuclear technology, healthcare, geology, chemical science, material science, archaeology, and environment. So it's a widely it can be used. Like a few examples is given here. Arsenic is very sensitive by neutron activation analysis. Now, any arsenic entering into human body normally accumulates in the roots of hair and moves along the length of the hair as it grows. So now normal growth of hair is around 0.35 millimeter per day. So one can analyze the hair by NA to arrive at the arsenic amount, and this analysis would be very useful in case of a person dies of arsenic poisoning, say. So then by cutting the hair into small pieces, the distribution of arsenic as a function of length also can be done, from which you will be able to know when the arsenic is being ingested by the person. So now you can see in the example the normal, while normal hair, normally the concentration will be around 0.8 microgram per gram. So any value access to this is considered as dangerous. So it is reported that 10.4 microgram per gram of arsenic was found in the hair of Emperor Napoleon, who was being, it is like in the history, it is there that he has been died because of arsenic poisoning. So the sectional analysis of hair by NA can indicate approximate date of arsenic poisoning. So this is the beauty of NA. So from where you can know, and arsenic is very, very sensitive by neutron activation analysis. So analysis of unknown powder, once the analytical chemistry division has received some unknown powder from customs, which has been finally analyzed by 3 different techniques, EDXRF, then it has been done by NA, and then it has been done by XRD. And from all these 3 methods, it has been confirmed as iridium metal, which has been smuggled through customs. So now there is Gonset residue analysis. Previously, there is a central forensic lab. Few persons are there at analytical chemistry division of BRC who are routinely doing this type of forensic samples by neutron activation analysis. So in Gonset residue, the marker elements are barium, antimony, and copper, which are being analyzed by neutron activation analysis. You require very small amount of sample, and also the sample is non-destructive because your its geometry or anything as an evidence, it is not getting lost by use of NA. So therefore, it is very important technique for this type of sample which are of legal importance. So these are gamma spectrometry showing the lines of barium, and this is the barium, zinc, antimony, and here it is sodium lines. So this is the gamma spectrometry. Now source correspondence study also, if 2 type of inks are there for different legal document is there, and so you can, by analyzing the ink, you can identify them whether they are from the same source or different source. You can see this is the typical gamma spectrum of one ink, and this is the typical gamma spectrum of another ink. So you can see there are difference in this. Here lanthanum peaks are available, but here no lanthanum peak is there. Therefore, you can tell that these inks are of different sources, are from different origin. The geological sample also, like, you can do by this, like you can see now gold has been analyzed in a sample from Karnataka region, which is expected to contain like gold, and all the 3 methods, because it's a complex sample of some soil sample. So you have all the 3 techniques have been tried, and you can see the values are quite close to each other. The gold concentration in ppm. Now, let us see the next one is the X-ray fluorescence spectrometry. So, X-ray are a small part of electromagnetic spectrum. These are short wavelengths electromagnetic radiation produced by the deceleration of energetic electrons and the electronic transition within the atomic orbital itself. So, X-ray propagates at the velocity of light. Their wavelength ranges from 10 nanometer or to 1 femtometer as shown below. So, these are the for X-ray region, this wavelength, energy and frequency. So these X-ray are also can be used for analytical purposes. How? Just we will see below. So now these X-ray were first discovered and documented by Röntgen in 1895. So they are also known as Röntgen ray. So immediately after their discovery, X-ray were widely applied in medical and industrial field. So the basis of qualitative and quantitative X-ray spectrometrical analysis was established by the English physicist Moseley in 1930. So now you can see the basic, what is the basic principle of XRF or X-ray fluorescence spectrometry. Let us see here. So XRF is a non-destructive analytical technique. Again, like NA, it is also a non-destructive analytical technique used to determine the elemental composition of materials. Now here I can stress upon that in your in many jewelries of the carat meter, whatever has been put there to check the carat of your gold is nothing but this XRF technique. So you just have seen that your gold ornament will be directly put in the instrument, and then they can check the purity of the gold of your ornament, and that is non-destructive. So now it contains. The principle is that a high energy X-ray source irradiates the sample, causing inner cell electrons in the atoms to be ejected. Like you can see here, this electron is getting ejected, and then the removal of inner electron creates vacancies here. Vacancies are being created which are filled by outer cell electrons. So now this vacancy can be filled by when the outer cell electron will be traveling here. Outer cell electron will travel here. So this will be filled. So this transition releases energy in the form of X-rays. Now this is the X-ray. This is the X-ray and are characteristic of the element present. So now detection, the emitted characteristic X-rays are detected and analyzed to determine the energy and intensity, now which corresponds to the type and amount of the element in the sample. So this is the pictorially shown how X-rays are being formed. The characteristic X-rays are detected, and then energy relates to the identify the element, the energy of the X-ray, whatever has been produced there are used to identify the elements, and the intensity of X-rays quantifies the element. So these are the two terms like energy and intensity. These two are being used to identify and quantify the elements. The typical block diagram of your X-ray spectrometer, and the various components are the source is there. Now the sample holder is there. So you have to a detector and then processing unit. So these are the, and for any instrument, these are the actually basic things which is required. And here also it's the same thing. So X-ray source, sample holder, detector, and processing unit. Let us see one by one just what are they and how they can be used. Now, a common X-ray source can be X-ray tube. What is it? It is a high intensity and versatile. So electrons are accelerated from a cathode to strike a metal surface, metal anode to generate X-rays. The target normally here the cathode material are typically copper, molybdenum, tungsten, rhodium, or silver. So the choice of an anode material depends on the application. Now advantages are adjustable power output and long lasting and efficient. So disadvantages are requires a high voltage power supply. So this is the X-ray tube which can be used as a X-ray source. The second one is radioisotope source. For example, americium-241 or iron-55, cadmium-109 or cobalt-57. They also can be used as a source of X-rays. Now radioactive decay produces X-ray of specific energy. Now the application is used in portable or low power instrument for specific elements. So advantage is compact and cost effective. No external power needed. You can be take this to field for use. And now disadvantages are limited lifespan due to decay. Now strict regulatory handling requirements are there because you are using a radioisotope as a source. So your instrument itself contains a radioisotope. Therefore, the regulatory handling requirements are very stringent. The third one is the synchrotron radiation source. So now electrons accelerated to near light speed in a synchrotron, which is like emit highly collimated and intense X-rays. So application are in advanced research requiring high resolution analysis, and also you can achieve very low, like very good detection limits, like material science, biological studies. Advantage is extremely high intensity and tunable energy, ideal for detecting trace and ultra trace elements. Disadvantages, expensive and requires specialized facilities. So there is a facility at CAT Indore. It is having a synchrotron radiation source where in case for XRF, you can go up to PPT level of detection limit. Now, key consideration when choosing an X-ray source are that element range. So select based on the element of interest, a sample type, adopt source intensity and energy for solid, liquid or thin films. Instrument type, portable XRF units often use radioisotopes, while benchtop instrument normally X-ray tubes are used. And for synchrotron radiation, you have to go to the synchrotron site for using it. Now, sample holder, also there are various types of sample holder, which is a critical component in X-ray spectrometer that ensures proper placement and alignment of the sample for accurate analysis. Its design depends on the type and state of the sample being analyzed. Now, for solid sample used for flat, rigid samples like metal, ceramics, or rocks, usually made up of inert material, for example, aluminium or plastic, which are transparent to these X-rays. Now, sequence the sample to prevent movement during analysis. Now, application is analysis of metal alloys, coins, or geological samples. Now, there is a circular sample holder for pressed pellets or soil or powder. So, soil or powder also can be pressed, and bead can be like pellet can be made out of that. Now, powder sample, you can directly do powder sample also in your instrument. So now the design for powder sample like ores, cements or pharmaceuticals, the powders are pressed into a pellet using hydraulic press, or alternatively powders can be placed in a cup with a support film like either mylar or polypropylene film are used because they are transparent to these X-rays. Now, application is elemental analysis in powder material. You can do this. Now, third one is liquid sample holder. So, use for aqueous or organic liquid samples. Now, feature is specialized cell with thin X-ray transparent film like mylar or Kapton. Prevents spillage and evaporation during analysis. Application is analysis of heavy metals in water or trace elements in biological fluids. You can directly do this using this sample holder. Now, thin film holder are there for thin films or coatings on a substrate. Now, hold the film flat to avoid wrinkle or fold. And then application is analysis of surface coating, paints or thin layer. You can use this type of sample holder. And also there are rotating sample holder where your sample holder will rotate slowly so that how it helps, it will help you to if the sample is inhomogeneous, then you can improve the signal by rotating the sample. So it will sample various, like if your sample is rotating like this, so you continuously you will be measuring at different places, and finally you can take the average of all this signal. So it will give you a better average value of the total sample, and this is helpful when it is not a homogeneous sample. So now the factor, what are the various factors you have to keep in mind while selecting a sample holder is that whether your sample is solid, powder, liquid or film. Now ensure whether it is homogeneous or not, because ensures even X-ray exposure across the sample. Compatibility must be chemically inert to avoid contamination or reaction with the sample. And now transparency of X-rays. Materials like mylar or Kapton are used to minimize the X-ray attenuation. Now, what are the various type of detectors used in your XRF? Now, detectors is a critical component of an XRF spectrometer, and it is responsible actually for capturing and converting emitted X-rays from the sample into an electrical signal. Because as you all know from the first class, initial class also, we have seen that there is no detector which can count your photons. Like photons could not be measured like that. So everywhere, wherever there is a photon as a signal, then you have to convert it to an electrical signal or voltage signal. So here also the detector work is that only to convert the X-rays into an electrical signal for analysis. Now the choice of detector significantly influence the resolution, sensitivity and overall performance of your XRF spectrum. So there are various types of detector, like gas field detectors are there, which are normally known as proportional counters. Now detects X-ray by ionizing gas molecules. that is argon in the detector chamber. Advantage, fast response time and cost effective. However, limitations are there. Low energy resolution, best suited for wavelength dispersive XRF or WD XRF. Now there can be scintillation detectors. Now converts X-ray into light via a scintillator, that is sodium iodide thallium, which is then detected using a photomultiplier tube. Advantages are high sensitivity for higher energy X-rays. Limitations are limited energy resolution, mostly used in WD XRF for detecting high energy X-rays. Then comes like semiconductor detectors, which are normally widely used in EDXRF and all. So this is the silicon drift detector, SDD. So X-ray creates electron hole pair in silicon, which are collected and measured. Advantages are excellent energy resolution, around 120 to 150 electron volt at manganese K alpha lines. The fast response and ideal for energy dispersive XRF. Now application is trace element analysis, environmental studies, industrial application. Limitation is that similar to STD, but now another one is lithium drifted silicon detector or SILI detector. Now the similar to STD for all the case, but the uses lithium to improve the sensitivity. So now it requires, because of lithium dope, it requires cooling by liquid nitrogen for operation. So you have to do that. Otherwise, the fourth one is cadmium telluride detectors. Principle is similar to silicon-based detectors, but made from cadmium telluride or cadmium zinc telluride. Advantages is again effective for high energy X-rays greater than 20 keV. Now you can see here it is only EV, whereas it is keV. So operates at room temperature. Application or analysis of heavy metals like lead and uranium. And there is multi-channel analyzer. The principle is that combines signal from multiple detectors to analyze a wide energy range. Advantage, speeds up data acquisition, enhanced element detection across a broad spectrum. Application is used in advanced systems for high throughput analysis. So that is the multi-channel analyzer. Now you can have this table to compare all these detectors. Now key features of a detector is the energy resolution. So the ability, like all the detectors can be classified based on these four things actually: energy resolution, detection efficiency, noise reduction, and temperature sensitivity. So now you can see the gas filled types of detector. All these detectors, whatever I have told, has been tabulated here with their features tabulated in the table, and you can see the SILI detector has very good everywhere. So now advantages and disadvantages of XRF. Now it is a non-destructive analysis. The sample remains intact, making it ideal for valuable or limited samples, like any historical artifacts is there, gemstones are there, or your ornaments are there. So it can be remain as such. Now rapid and simple operation. So minimal sample preparation, quick results with minimal manual intervention is there. Then wide elemental range. So detects elements from sodium to uranium, can analyze concentration from ppm to 100% also. So there is a wide range of concentration. Versatile sample type. It is suitable for solids, powders, liquids, and thin films, as you have seen. For each of these things, they have different sample holders. So what is different is only sample holders. So you have to change your sample holders from sample to sample. Now quantitative and qualitative analysis is possible. High sensitivity and precision is there. So minimal waste generation, no need for reagents or hazardous chemicals in most of the cases. Now automation and portability is there. So you can have portable XRF which uses the radioactive isotopes as their radiation source. You can go take it to field for your mining or environmental studies. And long-term stability, the instruments have stable calibration over an extended period. So like in case of AS or ICP, you have to calibrate them. Now spectrophotometry, you have to calibrate the instrument every day. But here it is, calibration can stand for long time. So now disadvantages are also there. Limited detection for light elements. There can be matrix effect, like you see light elements like lighter than sodium. For example, hydrogen, helium, lithium are difficult to detect due to low fluorescence yields. So special instruments like helium purge or vacuum chambers may be required. So matrix effects, elemental signals can be influenced by the sample matrix, leading to potential inaccuracies. So requires matrix mesh standards for correction. Surface analysis, so when your X-ray are falling on your sample, it can penetrate only to few micrometers. So depth analysis is difficult in this type of analysis. So lower sensitivity for trace elements compared to other techniques like ICP-MS, its sensitivity is less. Cost of instrument is very high. High initial cost for advanced XRF instruments. Maintenance and consumables are also highly costly. Now interference, overlapping peaks in the spectra, for example, K alpha of one element may overlap with the K beta of other. So it requires deconvolution algorithms or advanced detectors. Now sample preparation for powder is difficult. You have to press it into pellet that will give you, though there are powder sample holders are also there, but then if you do it in a pellet form, then it is good. So, or you can form some fused beads. Fusion machines are there also. You can make subject your sample to very high temperature and pull it down by pouring it in some cast so that it will form a bead. Say like round circular bead will be forming, which can be then directly put into your instrument. Radiation safety, again, X-ray pose potential safety hazards, so requiring proper shielding and handling protocols are required. Not suitable for organic compounds because XRF provides elemental analysis and cannot identify your molecular or structural information about your organic compounds. So these are the disadvantages. So now, thank you. So this is the last of the lecture, and then again, this is a picture of the new Apsara reactor, which has been commissioned recently, which is being used for irradiation of your sample for neutron activation analysis. So now, any question from anybody? Now today I was preparing your question paper, so it will be a multiple choice type of question. And maybe some fill in the blanks or such things. So if any query you are having, then you can ask. Otherwise, finally you have to evaluate and submit your assignment. Thank you.